Okay, so last week, in the last lecture, which was on Tuesday, we started counting winding numbers of curves around points. And I said that I was going to try and tie this into the concept of winding number in complex analysis. And in particular, I want to show today how to compute the winding number for a curve and how this can be used to generalize the Cauchy formula. So I'm going to just state the generalized Cauchy formula for computing an integral. And then I'm going to use this to write down something called the principle of the argument, which has to do with the counting of zeros and poles in a particular function. This will be useful. It is useful in various contexts, and in particular in the context of the mathematical physics of solitons. For those of you who have done the mathematical physics third year course at UCT, these words should be quite familiar, but perhaps not cast in this particular language. Okay, let me start by asking if there are any questions, particularly logistic questions. I see a few new people in the audience. Welcome. The details of how the assessment works and the course structure was all given in the last lecture, but I also think I included it on the Vula information page. If you don't have access to that, just let me know. For anyone else who wants a quick reminder, the course runs on Tuesdays and Thursdays at 11 on Zoom, this particular Zoom room, and it stays this Zoom room for the rest of the course. The assessment for the course is made up of problem sets. I'd like to say weekly problem sets, but it really depends on how much material we cover. So as soon as we've covered enough material, I'll give you a problem set to work on. The problem sets are not your typical, well, we've done X, we've done some examples with X, and here plug some other numbers in to see if you understand it, because I don't really believe that tests your, that doesn't develop your understanding of the material. So you'll find that the problem sets are slightly different from the kind of problems that we've solved in the class, and in a sense complementary. And so it's really kind of important that you do them because it gives you an idea of what it is you actually understand from the course material. Now, in addition to those problem sets, my courses tend to be littered with quick calculations. So these are calculations that shouldn't take you a lot of time, but they're kind of crucial to progress further your understanding of the course. So, you know, it's certainly self-contained, and you can certainly follow the lectures without doing them, but you'll learn a hell of a lot more by doing them. And they're really quick calculations. They shouldn't take you more than a couple of minutes. And they're in many ways filling in the blanks in the steps that go from parts of different calculations to other parts. And then in addition to the problem sets, which will count 60% of the class mark, there is a final take-home exam, and I prefer take-home exams to any 2-hour or 3-hour exams, because I can really test your understanding of the material with the take-home exam. So typically in my courses you get a weekend to work over the exam, and then this is followed up, and that counts 30% of your final mark, and then there's a 10% oral exam that follows on from that. And the oral exam will usually be myself and another member of staff in a discussion session with you at the end of the course. So again, any questions? Okay, if not, let's begin with today's lecture then. So each lecture will also start with an outline of what it is we're trying to, what I think are the learning points for the course, and we'd like to tick off all of these things as we go along. All right. So what I ended off last time with was the statement that the function w of z, which is given by 1 over 2 pi I times the closed integral over some contour C of dz over z minus zi for some point zi in the complex plane. And you could just regard this as a planar function. So you're integrating 1 over z, which is just log of z, and then I have to evaluate that on the boundary, and the boundary in this case is the curve C. And what this does for you is it counts the change in the total change in the argument of the function z minus zi as the z, the complex number, traverses whatever curve C around the point zi. So in this sense, the function w of zi, given by that integral, counts how many times the curve C winds around the point zi in the complex z plane. Now, this notion of winding number, of the times you go around a particular point as you traverse a curve, allows us to generalize what you would be familiar with as the Cauchy residue theorem. Now, what kind of generalization would you expect for the Cauchy residue theorem? Well, you're familiar already with doing integrals over contours that look like this. These are what we call simple closed contours. And these simple closed contours are closed. They're closed in the obvious sense of the word closed. And they're simple in the sense that they don't self-intersect. So we're not talking about, doing an integral over something like a figure 8 curve, for example. We're talking about simple closed curves. Okay. Now, if I assume all the usual axioms for Cauchy's theorem about the function, its convergence, its definition on the complex plane, etc., I can now generalize this and allow the curve C to be a non-simply closed curve. Okay, so by this, I mean that we're going to be able to extend the definition of the curve to something like a figure 8. Okay, and the only difference here is this weighting factor of counting of the winding number that enters the Cauchy residue formula. So typically in the Cauchy residue formula, you learn that if I give you some function,
I don't think we can see
and I
your
integrate.
annotation.
I'm sorry?
I don't think we can see your annotations.
Can you not see the annotations? I can see it on my.
Yeah, now
Can
it is
anybody see?
visible.
I just the annotation was
only available. They only just
Sorry?
became visible. They only just became visible.
Okay, so there's a lag.
I think maybe you just didn't press like enter on your, or I don't know. Maybe you just didn't. I'm not sure.
I don't. I'm writing it real time.
Okay.
Okay, so the lag is a little bit of an issue, but I'm using something. Let me ask you something. Can you see if I do this? Can you see it?
Oh, now we can. Yeah.
You saw that straight up. There was no lag.
Yeah.
Okay.
Okay.
That's good to know. I will use that in future.
Sorry, we should have let you know that we didn't see anything. I kind of was just like following, like imagining it, but I probably should have let you know that I hadn't seen anything.
That's fine. If you're using your imagination, that's good too.
We'll let you know if we don't see it all.
Okay. So thanks for pointing that out. Let's see how this goes. I'm using software that just got updated, and Nitin told me that when I write, it kind of appears in chunks with some lag, and I realized that the reason it does that is because it only registers new input as I lift the pen off the screen, and so if I'm writing in cursive, I tend to write a lot before I lift my pen off the screen, and then you just see a chunk of it. So that's likely why it's happening. But let's just keep track of this, and I'll see how it goes. Okay, so we have this generalized Cauchy formula. And the generalized Cauchy formula says that if I integrate this function f of z around the complex, around the contour C on the complex plane, then typically this is just 2 pi I times the sum of the residues of the function enclosed by the contour C. Right? This is the standard Cauchy formula. When I add to this weighting factor, if I weight this by the winding number, then I get what's called the generalized Cauchy formula. And the generalized Cauchy formula allows me to compute integrals on non-simple curves like this one, for example. Okay, so this is what we're going to do, and this formula here is what we're going to call the generalized Cauchy formula. Okay, any questions?
Yes, I have a question.
Sure.
Is that weighting number W of Zi always equal to 1 for simple curves?
Yes, it's always equal to 1 for simple curves. Okay, and that's because a simple curve will as you traverse a simple curve, it goes around the point in question, in this case, any of the poles, just once.
Right, cool.
Okay, it also manages to count for you what happens if you go around the curve in a negatively oriented sense, because in that case, the winding number is -1, and that minus is immediately counted. Does that make sense?
Indeed, indeed.
Great.
Thank you.
Good. So let's do an example. So the example I would like to do now is an integral that you probably have seen before. This is the integral of 1 over z squared minus a squared, and I'm going to take a to be some positive number, and I'm going to take this curve C to be a complicated looking curve that you will definitely have not seen in a beginning course in complex analysis, right? So the curve C winds around A and then links back again like that, okay? And we want to do the integral, we want to carry out the integral over this particular curve. Now, let's define the function f of z as 1 over z squared plus a squared. And this function has two poles. The poles are at z equals plus or minus a. In other words, they lie on the imaginary axis at z equals plus ia and z equals minus ia. Okay. And I can compute the residues quite easily at this at each of the pole. The residue of f at plus or minus ia is just 1 over 2z evaluated at z equals plus or minus ia. And if I substitute that in, then that tells me that the residues at each of these poles is just plus or minus 1 over 2 ia. Okay? So having calculated the residues, if this was a simple curve, I'd just add the residues, multiply by 2 pi I, and then I'd get the value of the integral. In this case, I have to count the winding numbers in order to add in the weighted formula. So the winding numbers work like this. So let's consider the point minus ia. And let's start here. And let's see, actually, right. So if I start here and I traverse this curve once, the question is how many times do I go around the point minus ia? And the answer is once. Let me do that again. So follow the laser pointer. It starts here. How many times do I go around the point minus ia? As I traverse the curve, it's just once. By comparison, if I start, let's say here, and I ask how many times do I go around the point plus ia, that's once and twice. Can you see that?
Yeah.
Good. In other words, the winding number of the curve around the point, around the pole at minus ia is just +1, and the winding number of the curve around the point around minus ia is +1, and around plus ia is +2. In both cases, I'm going around the curve in a counterclockwise sense. We said that counterclockwise was taken to be positive, so that explains the pluses, +1 and +2. And then if I count the number of times I go around the curve, I get winding numbers of +1 and +2, respectively. So if I take that and I plug it into the generalized Cauchy theorem, that says that the value of the integral, this integral here, is 2 pi I times 2, that's that 2, times the residue at plus ia, minus and that minus is coming from here, from the value of the residue, 1 over 2IA, and the total then is pi over A. Is everybody happy with this?
Yep.
Good. I'm going to take anyone's answer when I ask questions like, does this make sense, or is everybody happy with this? Anybody piping up saying yes, I'm going to take that as everybody's happy with it. If you are unhappy with something, please do unmute yourself and ask the question, and I'll be very happy to answer the question. Okay, so that's a simple example of an application of the generalized Cauchy theorem. In general, okay, so now we're going to have to, let's see how this works. Okay, can you see the point that I've made there?
Yeah. The
So
square.
Okay, and the writing is appearing?
Yeah.
Good. So in general, if I have two contours, let's say C1 and C2 are two contours, two closed contours, let's take that back, two closed contours, then the following is true. If I calculate the integral over C1.
Something's not going well with the screen now. It's like halfway in between two, like a clear white window. Okay, there we're back.
Is it okay now?
Yeah, I think so.
Hold on. Let me see if I can sort that out. Okay, so let's see how this goes. So if C1 and C2 are two closed contours, then if I calculate the integral of the same integral that we've done, z squared plus a squared over C1, and I calculate the integral of z squared plus a squared over C2, the difference between them is some integer multiple of pi over a. And the integer is related to the number of windings of C1 and C2. In other words, this is just n times pi over a, where this guy n is related to the number of windings of C1 and winding numbers. It's related to the winding numbers of C1 and C2. So this is an integer that's related to the winding numbers of C1 and C2. Is there any problem with the screen, or is it still good?
No, we're getting it. Thanks.
Okay, good. Okay.
Okay, now I don't think we are.
I'm not writing anything.
Oh, okay.
Sorry. Okay, good. So the winding numbers, it would seem, have something to do with the poles of the function in question. And whenever I have complex valued functions that have poles, simple poles typically, I'm talking about a class of functions that are called meromorphic functions. So meromorphic functions have a number of properties that are essentially topological in nature. And I'd like to explore a little bit of this going forward. So winding numbers correspond to meromorphic functions. And meromorphic functions are analytic everywhere except at some finite set of poles. So actually, it doesn't have to be finite, it could be some countably infinite set of poles. Okay. And meromorphic functions are very important when we try and study topological things in mathematical physics. So let's unpack this a little bit. Okay, so suppose I have some meromorphic function f of z in some region, let's say D on the complex plane. So suppose that f of z is meromorphic Is there a question? In some region D on the complex plane. Okay. And that D has boundary, which I'm going to denote by partial D, just keeping in notation that you may be familiar from complex analysis or from differential geometry. And I'm going to say that the boundary of D is some curve gamma. Okay, so just to be clear, if you're not familiar with the notation, this here is the boundary of D. Okay. In addition, I'm going to assume that this function f of z is not vanishing on the boundary gamma. And then I'm going to expand it near some point A that resides in D. Okay, so let's assume that f of z is non-vanishing on the boundary curve gamma, and expand near the point z equals a. Well, if I do that, what I'll find is that near z equals a, the function f of z, and I know this because all meromorphic functions have this property, can be written as z minus a to some power m times some function phi of z, where the function phi of z, remember the function f of z is meromorphic, the function phi of z, on the other hand, is analytic and non-vanishing. So analytic and phi of z, so phi of z, sorry, phi of and non-zero near z equals a. Okay. So I haven't told you anything about what this number m can be. And what m is will determine the structure of the function. But given that it's a meromorphic function, I want to try and read off some properties of the function by studying its expansion near z. Well, if I take a derivative of this function with respect to z, and I divide it through by z, then f prime of z over f of z can only be m over z minus a plus this analytic function, and analytic means I can take its derivatives to any order, divided by this. And here's the first exercise or quick calculation. So quick calculation number 1, show this. Okay. So what does this mean if f prime of z over f of z can be written as m over z minus a plus some analytic piece? Well, what it means is that this function f of z has a simple pole meaning a pole of order 1, meaning a z minus a in the denominator. It has a simple pole at z equals a, and the coefficient of that 1 over z minus a is, of course, the residue of the function f of z. So from this f prime of z over f of z equal to m over z minus a plus phi prime over phi, I can read off that f of z has a simple pole at z equals a with residue m. The residue is positive for 0 or negative number for a pole. So the upshot here is that f of z has a simple pole at z equals a with residue m. Okay. So let's take the function and integrate it over the curve, the boundary curve gamma. So if I integrate over gamma, we find the following. We find that, okay, and then because this is complex variable calculus, whenever I talk about doing integrals, typically I have to divide by 1 over 2 pi I. I have to divide by 2 pi I to make sure that everything is normalized properly. So let's go ahead and do that. So that's 1 over 2 pi I, because of course we want to apply Cauchy's theorem. Integral over gamma of f prime of z, which we've just worked out, over f of z dz. Okay. So what is this? This is just 1 over 2 pi I times the sum over the residues that are enclosed in gamma. Let's write that as the sum of the residues. Let's say the residues are I, closed contour integral of mi over z minus ai plus this analytic piece phi prime of z over phi of z, and I'm integrating all of this with respect to z, which I haven't left any space for. Okay. So what does this give me? Remember, the integral of mi over z minus zi was what we were calling the winding number. So this guy is nothing but I want to leave some space, so let's do it here. So this is nothing but the number of the winding number minus the number of poles. But actually, we have another expression for this integral of f prime of z over f of z. Why? Because if you recall, this quantity here, sorry, that was a super ugly bracket.
Sorry, can I just quickly ask, so is the P with the line going through it, is that the number of poles? Yeah.
Yeah, there's a line going through.
Okay, thanks.
Okay, good. So this quantity here, I know is the derivative with respect to z of the log of f of z. And so if I integrate that, I'll find that the integral over gamma of f prime of z over z, sorry, over f of z dz is equal to the change in log of z of, sorry, log of f of z as we traverse the curve gamma. So this quantity is, this denotes the total change in, so this is the change as we traverse the curve gamma. Okay. Now, I'm interested in the total change in log of f of z as I traverse gamma. If you think about writing f of z in its modulus argument form, and then ask what changes as you traverse the closed curve gamma, it is simply I times the change of the argument of f of z. In other words, if I put these two facts together, I get the following relation between the number of the winding number and, sorry, yeah, the number of, sorry, let me just double check something. Sorry, I explained that badly. Let me just take a step back to this point here. Is this showing up? Let's see. Okay, can you see that now? Can everybody see the laser pointer thing?
Yeah.
Okay, good. So let's go back to this formula. My bad. So what are we calculating in this expression here? This is the integral of this function m some number divided by z minus zi, z minus ai, plus the integral of this f prime of phi prime of z over phi of z. Now, phi is an analytic function, right? Phi prime then is an analytic function. Phi prime divided by some function that's not vanishing on the contour is still an analytic function. So what happens if you integrate an analytic function over a closed contour by Cauchy's theorem? Justin?
I can't remember.
This is what happens when you're unmuted. Anyone else? What happens if you integrate an analytic function over a closed contour?
Is it 0? I can't remember.
It is 0.
Okay, cool.
Right? The integral of an analytic function over a closed contour is 0. So this part is not giving me any contributions to the sum. So what's left? What's left is this part. And this part counts with multiplicity the number of poles and the number of zeros. If m is a positive number, then I'm counting the number of zeros. So that's what this n is. It's the number of zeros of the function f of z. And p is the number of poles of f of z. And the minus sign is because the number of poles contributes negatively to this number, and the number of zeros contributes positively to this number. So that's why you get this number of zeros minus the number of poles. So all of this is just to explore properties of this meromorphic function. So again, I have a meromorphic function. It's some function that has zeros, that has poles, but is otherwise analytic everywhere. Okay, so it's analytic everywhere except at some countably infinite set of poles that could possibly exist in its domain. The number of zeros of this function, where f of z is equal to 0, minus the number of poles is this integral. Okay, so now
Can you please repeat once again how n minus p comes?
Okay, so you with me that I don't get any contribution from this guy?
Yes, yes.
Good. So all I have to worry about is what's going on here. Okay? Yes? Anik?
Yes, yes.
Good. So this integral here, right, is basically saying sum over the residues of this function. And the residues of this function are with multiplicity the mi.
Yes.
Right? If the mi are positive, then I'm counting the number of zeros. If the ni are negative, I'm counting the number of poles.
Okay.
So if I count the number of zeros of the function f, then the total number of zeros is n. If I count the number of poles of f, the total number of poles is p inside this contour.
Okay.
Okay. And on the right, on the left-hand side, I have this integral. But we've just argued that this integral is nothing but I times the total change as I traverse the curve gamma of the argument of f of z. Okay? In other words, if I put all of this together, I'm learning that the number of zeros minus the number of poles is actually just 1 over 2 pi times the total change as I traverse the curve gamma of the argument of f of z. This relation here is an important one. So let's go and highlight it by putting a box around it. Sorry, let's put a better box around it. How's that? Okay, this is called the principle of the argument. And it's something that occurs quite frequently in the theory of optics and in scattering theory. And so it's worth making a note of what it's actually called. So this thing is called the principle of the argument. Okay. And the principle of the argument can be used, and that's what we're going to do with it just now. It can be used to derive a very useful result about holomorphic maps. Now, holomorphic maps are functions that map one domain into another domain, possibly one curve into another curve. And it'll be very useful for us in what we do a little later with solving differential equations. So let's use this now to derive this result. Okay, so to that end, I'm going to suppose that I have some holomorphic function. So W, which will be f of z, holomorphically maps some region omega in the complex plane to some other region omega prime also in the complex plane. And in doing so, it takes a simple closed curve and sorry, just give me 1 second. There's somebody at my door. Can you still see my screen?
Yes.
Sorry, it says my screen share is paused. Okay, tell me if the writing appears. Okay. And it maps a simple.
There's no writing.
Now? Still no?
No, not yet.
Okay, so let's stop sharing and try that again. Now, can you see the screen again?
Yeah, we can.
Okay. So this holomorphic map function maps a simple closed curve let's call it gamma in the domain omega onto another in general, this will not be simple. Yeah, this will not be simple in general. Curve, let's call this guy capital gamma. Capital gamma is in the domain omega prime. Okay. And I would like to ask the following question. So the question we would like to answer is the following. How many points in the region bounded by the curve little gamma are mapped into a given point in the, let's say, A in omega prime? So how many points in the region bounded by gamma, map to a particular point, let's say A in omega prime. Okay, that's the question. And my claim is that we actually have all the tools in order to see how this works. So let's draw some pictures to start off with of what all of these things look like. So suppose I have my initial point, my initial domain looks like this. Okay, so here's gamma, and it bounds a simple closed region omega. It looks like this. Okay, and this gets mapped to another curve, possibly non-simple, like that. Okay, so you can see that there's some non-trivial winding story going on in the curve capital gamma, and the curve capital gamma encloses some domain omega prime. And we want to know, given some point, let's say A, that lies, say here, say, how many points in this domain omega get mapped under the function W equals f of z, where the function f of z is holomorphic, in other words, it's analytic, get mapped into A. Okay, now A can lie in this region, or it can lie in this region, and we'd like to come up with a formula that counts both of these cases. Well, what we have on our hands here is, firstly, let me check, is the question I'm posing clear?
I think it is.
Okay.
Oh, I understand what you're asking. I don't know how to answer it.
You don't know how to answer it. Okay, that's fine. As long as the question is clear.
I have a question about the omega prime region.
Yeah.
Is that just the combined regions that lie within the one, say, loop of the non-simple curve and the other?
Omega prime is the entire region enclosed by gamma.
Right.
So gamma is a closed curve, possibly non-simple. Okay. So if we go back to the figure 8, for example, that I had much earlier, let me just see if I can find it. Right. So if I go back to this figure 8, okay, omega prime will be the entire grayish blue region. You with me?
Yeah, yeah. So that seems perfectly clear.
Yeah.
I'm just wondering if you were able to like take one of the lobes and sort of say the lobe there that encloses the point A. If you were to say move that so that half of it was, inside and half of it would outside, would the part that's outside still make up omega prime, if that makes sense?
No, I don't understand what you're saying. Say it again. That's just a statement
It's
about
very
my
hard to
understanding. It's
explain,
not a statement to put your question. Ask the question again.
So if you were to take the lobe that encloses the point A, right? So the circle
Yes.
within the bigger circle, and you were to move it so that half of it was inside the bigger region and half of it was outside. There isn't any, nothing changes there. It's still part of the same omega.
Yeah, whatever's inside. So okay, so how can you move the lobe? Well, imagine. So did you see what I did when I drew the curve? When I drew the curve, my curve went something like this.
Yeah.
Yeah, so that's the curve, right? So when you say move the lobe, so that half of it is inside and half of it is outside, it's not quite clear to me how you could do that.
It's like a rubber is twisted, so there is actually two planes or something like that.
I need to make a closed contour that encloses the two, right? So if I can enclose, are you saying something like, I don't know, like this?
Potentially, yeah. I may be
Okay,
a better.
then basically everything that's enclosed by this is still in omega prime.
Right. Okay.
Yeah.
Cool.
Good. Very good. So this is a counting problem where what we need to know is the number of zeros of the function f of z minus a. So that's my statement. If I want to know how many points in the region bounded by gamma get mapped to a particular point a in omega prime, then we need to know so what we really need to know here is how many zeros does the function f of z minus a have. In other words, I want to know how many values of z are such that f of z equals a. Right? So if f of z equals a, then I'm asking where, for what values of z is f of z minus a equal to 0. Okay? So the number of zeros
Is it 2 because it winds around the curve winds around that point twice?
Yes. You see where I'm going now?
Yeah, I think so.
Good. So the number of zeros of f of z minus a, as we've decided, is 1 over 2 pi I integral over gamma of precisely this function f prime of z over f of z minus a dz. And this guy is just 1 over 2 pi I integral over gamma of dw over w minus a. This is not mysterious. All I've done is I've changed variables because f of z is equal to w, and I've written, so if f of z is equal to w, then dw is f prime of z dz. Okay, this you've learned in first year when you change variables in doing an integral. So literally all I've done is I've changed variables in doing the integral. And of course, if I change variables in doing the integral, I have to change the domain of integration as well from gamma to the domain over which w is valued, which is capital gamma. Okay, so what? Well, now I look at this integral and it looks familiar because 1 over 2 pi I times closed integral over some curve of d omega of dw over w minus a is precisely what we were calling the winding number of gamma around a. So that's n of gamma over a, and this is the number of times that gamma winds around a. Okay. So that's a really cute result where it's taken what is essentially a counting problem, I'm counting the number of zeros of a particular function, and it's converted into a problem in analysis, complex analysis, where I can count the number of zeros by computing a particular integral. And that integral, it turns out, is related to the topology of the curve on the complex plane. In fact, it's related to the homotopy of the curve on the complex plane, and the fact that this curve winds around the particular point a some number of times. So if a lies inside this region, then the winding number is 2, and in fact 2 points in this domain will get mapped to that point. If a lies in here once, if a lies in any of this region here, where as I traverse gamma, I encircle that point once, then only 1 point in this domain gets mapped to that point. Is that clear?
Yeah.
Good. Okay, so that's what I wanted to say, and that was basically our warm up into reminding ourselves about some complex calculus. And in the next lecture, I'm going to start an analysis of ordinary differential equations again. But I guarantee you have not seen ordinary differential equations this way before. We're going to think about ordinary differential equations as differential equations on the complex plane, and we're going to see how to classify them, how to study their zeros, how to study the zeros of their solutions, how to study the asymptotic properties of their solutions, all preferably without doing the actual work of solving the differential equation. So we're going to try and write integral representations for the solutions of differential equations and show how the properties of these solutions are actually encoded in the coefficient functions in the differential equation themselves. Okay, are there any questions to end the lecture?